is a schematic for the structure, and you see here the memory array is in this part, and the vertical channel. So here is kind of a yellow line, or this pillar is a vertical channel. And then the green layers are the word lengths. And then at the very top, you have the bit names. And then here we have a stair of the word lengths, because we need to make a contact wire to each layer to control the word length. So here, those are the word length control. So in the initial design, from the top view, it's like 3F times 2F, not very dense. But this is the initial paper, but ideally you can get 2F by 2F from the top view, each pillar. So let's look at the cross-sectional view of this pillar. So essentially, this pillar actually resembles a string of the NAND flash, right? So if you have this circuit diagram, it's just a one-to-one mapping, like one string, but you just stack it vertically, right? And here this is bit NAND, and then this is the source NAND, and then the very first layer is the upper string select, and then the very bottom one is lower string select. So those are the normal transistors, you know, as for the even for the two-dimensional 2D NAND, at the end of the string, you have those two string select. And then in the middle, you will have this float, in this case, charge trap or cell. And you have this charge trap cell, and then you have this string. So basically, this is a cross-sectional view for the structure. Any questions? So it's very easy to understand if you think you just if you look at the circuit diagram, right? You have the NAND string, and then you just stack it vertically. So the other thing is that the channel is probably polysilicon channel, because when you make this channel vertically, you cannot have the single crystalline silicon from the substrate. So this channel is you refilled later with polysilicon. And then you need to understand the 3D circuit diagram like this, because for that array, if you draw the circuit schematic, then it will be something like this. Okay. So here, previous slide we show one string, and now you need to organize those strings into this 3D array. So let's say the end of the string on the top will be shared across this bit length, and then the upper string select here. Let's say in this example we show three strings. So you have those three upper string select lengths separately. But for the layer, let's say the word length, this will be word length 1, word length 2, something like that. So this word length control is for one layer. Okay. So this word length 1 is going to control all the gates in the same layer. So here you see the difference. This is collected. Okay. And for the lower string select is also collected. But with this kind of structure, you can do the decoding I mean in the 3D fashion, because if you want to locate one cell, it's still possible. First of all, this lower string select will control the selection of the whole block. Okay, this guy will control the whole block. If you want to read out, for example, then this one is on, then this whole block is selected. And then you need to locate individual cells. So for the bit NAND here, there will be decoder for this NAND. So you can locate to this bit NAND. You only have 3 strings in this example. Then we need to locate one string. Then you can use this upper string select to select one string out of those 3. So then you can locate this string. And then you can control the word line here to locate one cell in this string. So you can locate the individual cell in this 3D array. So any questions? Okay, so then let's look at how we do this staircase. Okay, here. This is for the word line contact. So for this 3D vertical channel NAND, as we discussed, we want to save the number of lithography steps to save the cost. And for the vertical channel, here, those pinners here, you just need one lithography step to define the channel, to define those holes, and then you just etch through. So you just need one lithography, no matter how many layers you have. Then the question here is for the word line contact. For those pinners here, those contact, you don't want each layer one litho step. You want, no matter how many layers, just one litho step. So how do you do that? This is the so-called this staircase word line access. The idea is that you first use one lithography. This is photoresist, and then you etch the first layer, first step in the staircase, and then you need to do this slimming, or sometimes called photoresist trimming. So you need to use some method to shrink the thickness of the photoresist. You don't do the second litho, okay? You just make the photoresist a little thinner. Then you do another etch, so you get a second step. So you keep this shrinking of the width of this photoresist, and then do one vertical etch. Then you get a step in this stair. So eventually you will get all the stairs. Of course, you need multiple etch step, but you just need one litho mask here. So as I said, the litho is the most expensive step in the fabrication.
The step size is also the same as the feature size?
So this is for the word line contact, maybe a little bit larger than the pinner, but it's still in tens of nanometer, or 100 nanometer at most.
So they can control the resist, not by patterning, they can have a few nanometer control.
You mean the step? Step may be tens of nanometer, yeah, or 100 nanometer. Later we can see the TM, and you can see how large is it. So you see, this staircase word line contact consumes the peripheral circuits, a peripheral area, because here this is your memory array. You have those pinners, vertical channel, and then you need to make this staircase for the word line contact, and then this is the wasted area under this staircase. Of course, this area will increase as you increase the number of layers, right, from this slide. Okay, so then this is the second paper from Toshiba in 2009 VLSI. and it's called P-shaped BiCS. So the only difference here is that, so if you look at this circuit diagram, so the idea is that previously the source NAND is at the very bottom substrate. Now we basically fold the string of the NAND, like the U shape. They call it P shape. I don't know why it's P shape. To me, it's like more like a U shape here. So basically, the string of that NAND string you fold into this U shape. So you can make the SL here instead of embedded at the substrate. So this will reduce the source NAND wire resistance, because you can use metal for this one. If in the substrate you have to use doped silicon as the source NAND. So this is improvement, reduction of the source NAND resistance. And another concern we need to care about is this etching profile. So when you etch this pinner, actually you drill a hole into the multiple layers. We will see the fabrication step in a minute. The key is that you have to make the etch is very vertical. If you have any angle here, you are going to lose your density. Right, so this multiple layers, this angle, or let's say this angle, you want to approach 90 degrees. If it's 89 degrees, then although at the bottom you may have like 30, 40 nanometer, at the top, if you stack like 100 layers, the top will become like hundreds of nanometer, and then the density is determined by the top, because this is another, let's say, another pillar, right? So you have to make this vertical, otherwise then the density will be lost. So this is really challenging for the fabrication, but somehow still the industry managed to make this better than 89 degrees. Okay, so this is the first paper by Samsung, 2009, again at the VLSI, and they call it TCAT structure. I would say very similar as Toshiba's initial design. There are some subtle differences, I think, in terms of the erase mechanism, but overall very similar. And this is the fabrication process for this TCAT design. And this is the gate last process. So what does this mean? So let's look at this process. I think the previous guest lecturer, maybe my postdoc already introduced some of those concepts, so we may have to go this quickly. So the idea is that for multiple layers, you need to first deposit multiple layers in this sandwich structure. So the sandwich between the oxide and nitride, multiple layers. And then you define your memory cell array region, let's say in the middle, and then you use 1D lithography to define those pinner, and then you drill a hole by etch. And then we need to cut the wear line out, and then form the staircase. So let's look at this detailed process here. So for example, firstly we have the oxide and nitride layer by layer, and then we dig this hole and then we refill this hole with the polysilicon as a channel. And then we need to separate the pinner, so we cut this out, means we etch. So after that, we need to remove the nitride. So this nitride area, this is like a sacrificial gate. We need to remove it by wet etch. So this is removed, or this is like a dummy gate or sacrificial gate. So you don't need it eventually. So you need to remove it, and then now you deposit your real gate stack. For example, your charge trap layer, and then the tungsten as the metal gate, and then you refill the gate because this gate region is open here, and then you need to refill it. Oops. Refill it, and eventually, and then you etch, and now this is your real gate. So you have some dummy gate first, which will be sacrificed, and eventually you get your real gates there. So this is the question.
Roughly how big is the size of the opening of poly channel?
Oh, that's a very good question. So it's about 50 to 60 nanometer. So we will talk about this point later actually. So the feature size for the 3D NAND actually is larger than 2D NAND. It's relaxed to be even in the first generation, I think 100 nanometer, the pinner, the diameter.
So all the deposition here is rely on, so it's like ALD.
All the yes, maybe the polysilicon channel, is by PECVD, I guess. But for the critical layers like the tungsten oxide, the charge trap layer, all of them are ALD. Otherwise, you cannot conformally fill this kind of structure. It's very tricky.
So what is the aspect ratio for the channel?
Yeah, that's a good question. So, as I said, so this, maybe when we look at the TEM image, and then you can tell. So the diameter is like 100 nanometer in the first generation, and then the height for each layer is roughly the same, I would say, 100 nanometer. Then how many layers? Let's say in the initial version is like 24 layers, so it's like 24.
So because during after your wet removal of your nitride, there's nothing supporting your channel, right? It's kind of standing free.
You are right.
And it could collapse.
Yes, you are right. So I don't know. I mean, how the industry manages this fabrication issues. So this is amazing. So this is the gate master process, the full process, and used by Samsung, Toshiba, SanDisk, I think also Hynix maybe. So let's go through this quickly. Again, first deposit oxide and nitride sandwich layers, multiple layers, depending on how many layers you need, and then you use lithography define the vertical channel, the pinner, and you then etch this hole, and then you refill the hole with polysilicon as a channel, and then you cut the word line, and then remove the nitride, this sacrificial gate, and then refill the gate, regrow the tungsten oxide, followed by the nitride charge trap layer, and then high-K dielectric, which is the interpoly dielectric, and then fill with the metal. Basically, you form the sonus, this Thanos structure, and then eventually you etch out. So this is the process. So you see here the channel is first refilled, and then you do the gate. This is a gate last. And then Intel and Micron use a different approach. It's still vertical channel, but the process is called the gate first process. So here shows the key concept. Again, we have the oxide and nitride multiple layers first, and then we etch. We still etch that hole, but then after we etch the hole, we will do the gate first now. So after the A step, and then what they do is they recess a little bit on the metal wires. I think here is metal and oxide instead of the metal like let's say nitride and oxide. So they recess the metal a little bit, and because this metal is the gate metal already there, and then we form this interpoly dielectric, and then do the floating gate polysilicon, because in this case it's floating gate, it's not charge trap. So this kind of blue is the floating gate, and then we refill this polysilicon here, and then etch out, and then grow the ternal oxide, and eventually fill the channel, the spinner with the polysilicon. So the channel is formed in the last step. We grow the gate first. So this is just opposite to the Samsung's approach. And again, this is the process flow. I will not repeat. So you can read this by yourself. So I would say the gate first process in general is easier. In terms of the complexity is there. So there must be some trade-off, I think, when Samsung use the gate last process. Okay, so this is a summary. All of them are vertical channel. The only difference is Intel and Micron use the gate first process, and the cell is this floating gate cell as a 2D NAND. All the other companies are gate last, and the cell is a charge trap, and it's like this Thanos actually structure, or variant of this Sonos structure. So any